Okay, thank you.
Here, Ricardo Chacartegui, the professor of the energy engineering department of the University of Seville, is the coordinator, and he's going to present us the project. Ricardo, the floor is yours. Ricardo, sorry, you are on mute.
Okay, thank you very much, Angela. Thank you very much to the previous presenters. I see the global presentation that everything is linked, because at the end the CSP approach is a collective. It's a collective approach, and from different point of view, we can see how contribute to the evolution of different technologies within the sector. So the Socrates Project, so it's a consortium that is composed by partners of all Europe. And first, I want to introduce the context, the main points that drive it to the concept and the main outcomes that we have had. Well, in CSP main research line, they have been previously commented, cost reduction regarding reducing the capex of equipment, or also having higher efficiencies. You're not watching my screen, isn't it?
No, okay, not yet.
Sorry, apologize. Yeah, I was.
Now we can see. Yeah, now we can see.
Please interrupt me. Well, the main. So let me show you the previous slide. Okay. So the main CSP research line are cost reduction with capex reduction of equipment, and also obtaining higher efficiencies, improving dispatchability with energy storage, and increasing the environmental sustainability of the plants. Within the energy storage system based on thermochemical energy storage, there is a number of different technologies. Not all of them are presented here. We have in this project going to the calcium looping, that is based on the decomposition of the limestone into calcium carbonate, into calcium oxide and carbon dioxide. Energy is stored in the chemical bonds, and when heat is required, missing these products, heat is delivered to form again calcium carbonate. A global scheme of the process can be seen here, in which calcium carbonate is decomposed in calcium oxide and carbon dioxide in the char process. This is a high temperature process at atmospheric pressure. It's a closed loop, but at atmospheric pressure, it requires temperatures about 900 Celsius degrees. The products are stored and can be stored for long-term seasonal storage. And when heat is required in the discharge for industrial processes or for power generation, they are missing in the carbonator, producing again limestone. This heat is delivered at high temperature, at atmospheric pressure. It can be as high as 800 Celsius degrees. The first concept was developed or was presented in this paper. Which are the advantages of the calcium looping applied to concentrated solar power? It has this pair calcium oxide, carbon dioxide. It has a high volumetric energy density at a high turning temperature. This is a challenge, but at the same time, it's an opportunity. It allows different strategies for solid storage at different temperatures. If at ambient temperature is used, thermal losses can be very low. It allows capacity. It has capacity for seasonal storage. It hasn't the problem that can arise in the most extended commercial, or in one of the two extended commercial applications, molten salts. One of the stronger points of the concept is that it's based on very abundant and stable materials. They are some of the materials more abundant on the Earth's surface. So they have low price, they are abundant and widely available, and they are relatively non-hazardous or contaminants. So they have the materials that we are using, we are considering this approach, have the characteristics for the large-scale deployment of energy storage systems. Besides, at the level of heat delivery, temperatures, very high temperatures can be obtained depending on the operation pressure. In our project, we are considering only atmospheric 1 bar, atmospheric pressure. It's a closed loop, but atmospheric pressure. But going to the higher pressure and higher partial pressure of carbon dioxide, the turning temperature increases. It allows also, playing with that, we can go to higher temperatures in the heat delivery. Besides, we have also obtained that depending on the temperature and pressure, the optimum regarding the reaction rate of the material moves at values of this that we present here for 3 atmospheres. It's around above 800 Celsius degree. The concept comes from the idea of looking for an energy storage system to integrate supercritical CO2 cycles and high temperature cycles. So it can be applied to direct integration with the challenges regarding particles and how it's integrated, and also in indirect integration and with challenges regarding how it can be, how the heat is extracted. Materials, and following with the advantages and opportunities, the materials and equipment, most of them are used at industrial scale. They are very close to cement. Many of them are very close to those used in cement industry, but in red I highlight here some that need to be, that are not available. Also, the closest CO2 Brighton cycle is not commercial, but it can be also highlighted as red. But this concept is very close to the cement industry in any case. This taking as an advantage and opportunity. And which are the main challenges identified? Well, we have particle solar receivers at high temperature, and we have to consider this is a big challenge, and we try to contribute with this project, giving answer to the open issues regarding how affects particles residence times, circulation, thermal gradients, and which are the key points for the scaling up for application of higher size. For instance, we are studying how to reduce this calcination temperature, playing with the partial pressure. This is the same graph that before, but changed the ASICs. So this partial pressure of this carbon dioxide, playing with the partial pressure, we can go to higher carbonation temperature and lower calcination temperatures. So it's a one way of playing, of obtaining lower temperature calcination and obtaining higher temperatures at the carbonation. We can use also helium or steam to dilute the CO2, and with additional challenges regarding separation, behavior of the particles, and so on. Regarding the main challenges, also we have the behavior of multi-cycled calcium oxide compression. So the calcium looping, it has been more advanced in carbon capture, and we have that these are the typical deactivation curves with the number of cycles. Which, related to this deactivation behavior, we have that the flows that solids that must be dealt are increased, and it penalizes the consumption, the parasitic consumption, and the global behavior of the plant. So we have identified that this deactivation is highly dependent on the design condition of reactors, materials, and processes, and the power plugging, and how the calcium, the CO2 penetrates in the surface and inside the material. So, summarizing the main benefits or the main characteristics of the calcium looping storage concept in CSP, So, as we say, abundant calcium oxide precursors, reactants and products can be stored at ambient temperature. We have that carbonation and heat delivery can be obtained at high temperatures, allowing high efficiency power cycles, gas turbines. The material allows high energy density to maximize storage capacity. There are equipment is available, or at least the knowledge is available in the widespread industries like the cement. So in our project, we try to analyze how is the behavior of the materials, how must be the design of components, how these components are designed. We don't try to make a beta system of a real plan, but to extract most of the information regarding the processes at the reactors, at the storage, the materials, movement, and at the different levels, at the laboratory level, at reactor level, and potential for scaling up. One very interesting thing that we identify at the beginning of the project is that if here you have the behavior of the activation of the material at a carbon capture condition. This is with CO2 concentrations around 50%. These are the typical ones of the coal power plant at the source. However, we are operating in the CSP application. We are considering closed loop circulation. So we have pure CO2, or if we add some additive or some additional elements. In any case, we have very high CO2 concentration, very high partial pressure, CO2 partial pressures. And we have that the deactivation of material changes completely. And here you see how it's a very good news. These are very good news for further development. The objectives: to advance in the knowledge of the calcium looping for thermochemical energy storage, to develop prototypes of different components and implement the integration in order to reduce the core risks of scaling up, generate new knowledge, and to identify and, if possible, to solve challenges associated. We have partners working on new materials, or very old materials, but analyzing their application, because limestone was applied more than 6,000 years ago. Analyzing the reaction, analyzing how must be the operation, the integration, the control, and how the systems are integrated. Everything is oriented to scaling up, and it can be applied. We have developed, first of its time, solar cyclone calciner with a beam down application in order to have enough temperature. In here, for the processes, we have a downer gravity closed loop calciner, system of an adjustment of this beam down application, an entrained flow reactor for the carbonator. All of them have been developed. We have installed in the place that we have here in the University of Seville. Here you have some images. Each one of them is oriented to obtain specific information related to the behavior of the materials and the components and the challenges for the design. This is a low TRL project. And here you have some photographs in the place that I'm currently. So here you have the cyclone calciner, the entrained flow calciner by gravity. Here you have the carbonator. Here you have the power block, some details. And here. This is the composition of the consortium. We have suffered, as everyone, the COVID-19, and I want to thank to the consortium, the efforts to be successful in this very complex period, and also to the European Union because of their understanding of the needs that we have had along this. Well, related to this, we have produced it, and you have data. This is a non-complete sample of published results in which different data are presented regarding integration and processes, materials, behavior, components, calcium looping perspective and challenges, and even some evolutions regarding the original concept, identify the opportunities with application in industry. Okay, and that's all from my side. Thank you very much, Angela.
Thank you very much, Ricardo. It's a pleasure. This is a very exciting project, and I think that all the consortium has made a very good job. Thank you, Ricardo.
One important thing is that Angela belongs to the Socrates consortium. So.
Yeah. I
reason she says
I'm
that.
not the person.
Okay, thank you.
Okay. So thank you, Ricardo. Well, now.